Okay, so welcome to the session 2, which is the other Zoom account that we're using. So the chair for this session is Debarga Banerjee. So Debarga, you are around, no?
Yeah, I'm here.
Yeah, okay, yeah. So yeah, you can start announcing the speaker and proceedings.
Good morning, everyone. So welcome to this ISC joint meeting. And our first speaker is Dr. Shaunak Deo from IISc. And he's going to speak of non-density of modular forms and pseudo-deformation rings. Shaunak, please.
Yeah. So thank you, Debaga, for the introduction. Let me share my screen. I hope I'm audible and everything is fine.
Yes, you're audible. And I can see your screen also.
Okay, thank you. So that's great. So again, thank you very much for the introduction and for letting me speak here. It's always nice to speak at ISER, even though virtually. So the title of my talk is Density of Modular Points in Pseudo-deformation Rings. So the plan for today is basically, I will just give some motivation for the questions I want to study. And then I will talk about, I define various objects that I'll be working with. Then maybe some history, then aim and setup, and then a description of main results. And depending on the time, I might say something about the proof. But because this is just a half an hour talk, I'm not sure if I'll get to the proof setup. Okay, so let's begin. Let's start with some standard notation. Okay, so let P be an order prime, F be a finite extension of Fp, which is finite field with P elements. W of F be the ring of bit vectors of F, and N be a integer greater than or equal to 1, not divisible by P. So bit vectors are just, if you take F to be Fp, bit vectors are just Zp. Otherwise, you take the unramified extension of Qp, whose residue field is F, and the ring of integer becomes the bit vectors. So if you don't know what bit vectors are, just assume they are Zp and F is Fp. Okay. Now we denote the Galois group of the maximal extension of Q, unramified outside NP infinity over Q by GQ and P. So you have this maximal extension of Q unramified outside NP infinity. It is Galois over Q, and that Galois group we denote by GQ and P. And we are going to look at representations of this Galois group. So let rho bar be a continuous odd semi-simple representation from GQ and P to GL2 of F, and we are assuming that the conductor is N naught, and we assume that N naught divides N. Okay, so it's a continuous odd semi-simple representation. So that means it is either irreducible or absolutely irreducible, or it is just a sum of two characters. Okay, and one of the basic, I shouldn't say basic, but one of the important results in number theory, which is due to Carré-Winterbugger, is that this rho bar actually arises from a modular eigenform of level n. So what do I mean by that? This means that there exists an eigenform f, such that if you take the p-adic Galois representation attached to f by Delhi /Shimura Delhi inside depending on the weight, and you look at a stable lattice inside this Galois representation, you reduce the lattice modulo the uniformizer, you get a representation over finite field. And when you so this uniform, so we are looking at p-adic Galois representation, so you'll get a representation over an extension of fp, and when you semi-simplify, you should get rho bar. That's what I mean by a rho bar arising from modular eigenform of level n. So this was Serre's conjecture. Okay, I should say that if rho bar is reducible, then it is very easy, because you just take corresponding Eisenstein series, and it is easy to see that rho bar is coming from an eigenform of level n, because it will come from an Eisenstein series. But when rho bar is absolutely irreducible, it was Serre's conjecture that it arises from a modular eigenform of level n, and Carré-Winterbugger actually proved it. So that is the hard part of this claim. But anyway, we do know that it is arising from a modular eigenform of level n. So it is natural to ask that if you take all the lifts of rho bar to W of F, or finite extensions of W of F, do they all also arise from modular forms? And the answer is no. All lifts do not arise from modular forms, because you can just look at the determinants to see why this is not true. When you look at the p-adic Galois representation attached to modular form, the determinant of that representation is some finite character times an integer power of p-adic cyclotomic character. But you can always, always twist it by a lift of the determinant, by lift of the trivial character, so that it becomes some finite character times some non-integer p-adic power of cyclotomic character. So obviously all lifts do not arise from modular forms of rho bar to finite extensions of W of F. So the natural question to ask is, does every lift of rho bar to a finite extension of W of F, does it arise from an arithmetic object or not? And that is, it's a natural question. We know that it does not arise from modular forms, but is there some other object, which sort of encompasses modular forms and goes further, and all these representations, whether they arise from that? And a natural candidate for such an arithmetic object is the p-adic modular forms, which are quote unquote p-adic limits of classical modular forms. Because they would give rise to Galois representations, and it is reasonable to expect that they would sort of count for all the lifts of rho bar to finite extensions of W of F. So a natural way to approach such questions is via deformation theory. And so one of the natural approach is that we can compare the universal deformation ring R rho bar of rho bar. So universal deformation ring will interpolate all lifts of rho bar to CNL WF algebra. CNL means complete Noetherian local, WF algebra. So they are just power series, quotients of power series rings over WF. So these are like sort of all the lifts of rho bar with the big p-adic Hecke algebra, which is acting on the space of modular forms of level n and all weights. So R rho bar is sort of interpolating all the lifts, and this big p-adic Hecke algebra, it is interpolating lifts arising from modular forms. And if you want to know if there is any relation between any lift of rho bar to finite extension of W of F and lifts of rho bar coming from modular forms, it is natural to compare these two objects, one which is parameterizing all the lifts and the other which is parameterizing lifts coming from modular forms. If you know some comparison, then you can conclude for sure that there is a relation, or maybe then, or if they are not the same, then you can say, okay, there are some lifts which have nothing to do with modular forms in a sense. So this is like a natural way to approach these questions. However, there is a catch here, that such a ring R rho bar, which is sort of interpolating all the lifts, it may not always exist. So when rho bar is absolutely irreducible, this universal deformation ring of rho bar exists, and this is due to Mazur. This is a landmark work on deformations of Galois representations. So when rho bar is absolutely irreducible, we are fine. But when rho bar is reducible, this ring does not exist in the sense of Mazur. There are some other variants, but this exact universal deformation ring in the sense of Mazur does not exist. So this is like, but when we started with rho bar, we just assume rho bar to be semi-simple. We never said it is absolutely irreducible or anything. So we would like an object which works for all the cases, which works for absolutely irreducible representations and reducible representations. So to do that, what we need to do is we need to consider a slightly different object, and that is the universal deformation ring of the pseudo-representation corresponding to rho bar, and we'll call this universal pseudo-deformation ring of rho bar, and we'll denote it by RPD rho bar. So I will just in a moment say what this pseudo-representation corresponding to rho bar is, but an important point to note is that when you go to the case of absolutely irreducible representations, the universal deformation ring, in the sense of Mazur, the universal deformation ring of rho bar is same as the universal pseudo-deformation ring of rho bar. Okay, so we are really considering, the right object here, because when you go to the absolutely irreducible case, which is about which we know more, it gives us a familiar object that we have, this R rho bar. So we are really studying their lifts when we are in absolutely irreducible case. So in other words, R rho bar is R rho bar PD whenever R rho bar is absolutely irreducible. So therefore, we are going to consider the right object to consider here is not the deformation ring of rho bar, but the pseudo deformation ring of rho bar, so that we can also study the reducible case as well. Now, what's a pseudo representation? Let me give you a quick summary of what a pseudo representation is. So roughly speaking, a two-dimensional pseudo representation. So we are only going to be working with two-dimensional pseudo representations. So a two-dimensional pseudo representation of a group G over a ring R is just a tuple of function which behaves like trace and determinant of a two-dimensional representation. It is not really trace and determinant of two-dimensional representation always, but it will behave like one. So let me make it precise. So if you have a topological ring R, then a two-dimensional pseudo representation from GQNP of GQNP over R. It's a tuple T comma D from GQNP to R of continuous functions, such that this D is actually a homomorphism of groups. So it lands inside units of R, and it's a homomorphism. So D is like determinant of a representation. So obviously you would expect it to be homomorphism. T of 1 is 2, so T is like a trace of a representation. So T of 1 is 2, and T is also central. So T of GH is T of HG for all G and H in GQ and P. And we have this slightly complicated identity that D of G times T plus T of GH is T of G times T of H for all G and H in GQ and P. This is sort of the only non-trivial condition. The other three conditions are very natural. So this is sort of the only non-trivial condition in a sense. So an obvious class of examples is that if I have a continuous representation from GQNP to GL to R, then the trace and determinant, this tuple, is a two-dimensional representation of GQNP, and we call it a pseudo-representation corresponding to rho. Okay, so this is when I said that I'll consider the universal deformation ring of the pseudo-representation corresponding to rho bar, I mean this pseudo-representation, trace rho bar, determinant rho bar. I will look at its universal deformation ring, which means it is interpolating all the pseudo-representation lifts of this residual pseudo-representation, which takes values in CNL WF algebra. So I will recall this object once again later. So we know what kind of object we should study on the algebraic side. So the pseudo-reformation ring, and now we'll define what Hecke algebra we want to study. And for that, we let MK and WF be the space of classical modular forms of weight K, level N, and Fourier coefficients in WF. And then we just take their sum inside the power series ring over one variable in WF using Q expansion principle, and we let this sum to be M of N comma WF. So that is just sum K goes from 0 to infinity, MKN of WF. So Mn of WF is just the space of modular forms of level N, which have Fourier coefficients in WF, but there is no restriction on the weights. We are taking all the weights. Okay, so it's a huge space. Usually we fix weights, but in this case, we are taking all the weights. We're just fixing the level and Fourier coefficients. Okay, and now we'll define a suitable Hecke algebra acting on this. So let P of N be the WF subalgebra of the endomorphism ring of this module, which is generated by the Hecke operators TL and SL for primes L not dividing NP. So SL is basically the operator whose action on weight K modular forms coincides with the diamond operator times L power K minus 2. But since we are varying the weight, this SL will have a different action on modular forms of each weight. So therefore, I'm denoting it by SL. So it is just so T of N is just a WF subalgebra which is generated by the operators TL and SL. But if you want to compare it with the deformation ring, it has to be local and complete and so on. You cannot just compare T of N with it, and T of N is sort of acting on all modular forms, and we are interested in modular forms which sort of lift rho bar or which are like eigenforms, linear combinations of eigenforms which lift rho bar. So we have to slightly modify this algebra. So to do that, we have to observe that there is a maximal ideal M rho bar of Tn which corresponds to rho bar. So we know that rho bar is coming from a modular eigenform of level N. So that modular eigenform will give you a prime of height 1. And when you put P inside it, it will P or a uniformizer, it will give you the maximal ideal M rho bar, which will denote by that maximal ideal will denote by M rho bar. And we let Tn rho bar be the completion of Tn at M rho bar. So this is the object that we would like to compare. Just to note that Tn rho bar is actually a complete Noetherian ring with residue field F, and it is also reduced. Okay, so this is the object we want to consider on the arithmetic side. And so just a notion that theorems which will compare this universal pseudo-deformation rings and Tn of rho bar and assert that they are isomorphic, they are called big R is equal to T theorems. If you know big R is equal to T theorem, what it says is that the universal deformation ring and big p-adic Hecke algebras are the same. And inside the big p-adic Hecke algebras, if you see the primes, which if you look at the formal spectrum and look at the primes which correspond to modular forms, modular eigenforms, they are dense because that's how the Hecke algebra is defined. And these dense points are called modular points. So this isomorphism would tell us that these modular points are also dense inside the universal deformation space of rho bar, because it is same as the space given by Hecke algebra. So that's why the title, that density of modular points in pseudo-deformation rings, it comes from here, that whenever we establish a big RST theorem, which just shows that Tn rho bar is isomorphic to R PD rho bar, it tells us that deformations coming from modular points or modular forms, they are dense inside the universal deformation space of rho bar. And therefore, for example, the question we started with, that what is every lift of rho bar to finite extension of WF, does it come from an arithmetic object? Then we can say that if the big RST theorem holds, then we can say that it does come from p-adic modular form, because it will be a limit of deformations coming from classical modular form. So by definition, it will come from a p-adic modular form. Okay, so to answer the question that we had posed initially, we have sort of reduced that question to the question of establishing when is RPD rho bar and Tn rho bar isomorphic. Okay, so this is what we'll be focusing from now on, and these theorems are also a key step in Emerton's strategy to solve Fontaine-Mazur conjecture. So so there are other applications of such theorems as well. Okay, so our aim from now on is we would like to establish big RST theorems, and there is a history for of these theorems. So let me quickly recall what we know. So in the famous Gouvier-Mazur infinite Fern paper, what Gouvier-Mazur proved is that every component of spec of Tn rho bar, it has Krull dimension at least 4. And as an immediate consequence, they proved that if rho bar is absolutely irreducible, then there is a surjective map from R rho bar to Tn rho bar, and it's an isomorphism when rho bar is unobstructed. Unobstructed means that the universal deformation ring of rho bar is power series ring in 3 variables. And it is clear that the second is an immediate consequence of first, just using the definition of unobstructed. So this was like one of the first big R is equal to T theorems that were known. Then Böckle improved on it heavily by proving that if rho bar is absolutely irreducible, then under some mild hypothesis, which are known as Taylor-White's hypothesis, this surjective map from R rho bar to Tn rho bar is also an isomorphism. I would like to note that in his theorem also rho bar is absolutely irreducible, but the other hypotheses are much milder than the unobstructed ones. And because we are in absolutely irreducible case, pseudo-deformation ring and deformation rings are the same. So that's why I'm just writing R rho bar and not RPD rho bar. Okay, so this was a major improvement on Gouvier-Mazur's result, but Gouvier-Mazur's focus was mainly on studying the Hecke algebra. And this big RST was just an easy consequence of their study. And later on, recently Patrick Allen has extended results of Böckle to prove big RST theorems in the context of polarized Galois representations for CM fields and also for Hilbert modular forms under some hypothesis. But he also assumes that rho bar is absolutely irreducible. So nothing is done for rho bar reducible. So that is precisely the aim of our study. So we would like to explore big RST theorems for reducible rho bar. They are known for irreducible rho bars, and we would like to explore them for reducible rho bar. So let me just quickly recall the setup. Now I had this rho bar from GQNP to GL2F. It was odd and semi-simple, and now I'm going to assume that it's reducible. So therefore it is sum of two characters chi1 bar and chi2 bar, which are from GQNP to F star, and I let chi bar to be chi1 bar times chi2 bar inverse. I let n naught be the arcing conductor of rho bar, and we had assumed that n naught divides n. So again, because rho bar is modular, it is coming from a modular Eisenstein series of level n, it will define a maximal ideal m rho bar of Tn, and we let which contains P, and we let Tn rho bar be the completion of Tn at m rho bar, like I just did a couple of slides ago. And I let R rho bar PD be the universal deformation ring of the pseudo-representation attached to rho bar. So it is the universal deformation ring of the pseudo-representation tres rho bar comma determinant rho bar from GQNP to F in the category of complete Noetherian local rings with residual field F. So what does this ring do? It interpolates all pseudo-representations which are taking values in objects of C. So which are taking values in complete Noetherian local rings with residual field F, or in other words, the rings of the form quotients of power series rings over W of F, and which lift trace rho bar and determinant rho bar. So instead of parameterizing or interpolating all the lifts of the representations, I'm looking at an object which interpolates lifts of the pseudo representations. Okay, so pseudo representation lifts. Tuple of functions which behave like trace and determinant of a function. And this existence is due to Chenevier. I should mention that this whole notion of pseudo representation is Chenevier's notion. So I think initially Weiss had a notion of pseudo representation, then Taylor improved upon it. Then Nissen and Rukia developed a theory of so-called pseudo characters, but it was still missing some cases. And at the end, Chenevier came up with this theory of pseudo representations, or of what he calls determinants. And it sort of tied up everything nicely and made the theory complete. Okay, so I just wanted to mention that all the notions I'm using here are due to Chenevier. So the existence of this universal pseudo-deformation ring is also due to him. So this universal deformation ring is also a complete Noetherian local ring with residue field F. Okay, yeah, so I would like to move on. And I would also like to say that there are n-dimensional pseudo-representations, but they are not as user-friendly as two-dimensional ones. So this nice user-friendly definition of two-dimensional ones that I gave, it's not available for n-dimensional pseudo-representations. But fortunately, we are just over two-dimensional ones, so we are saved in a sense. Okay, so this is the setup that rho bar is reducible, Tn rho bar is the corresponding Hecke algebra, which is completion of Tn at m rho bar, which is maximal ideal corresponding to rho bar, and R rho bar PD is the universal pseudo-deformation ring of rho bar. So it is the universal deformation ring of the pseudo-representation plus rho bar determinant rho bar. Okay, so now I'd like to compare R rho bar and Tn rho bar. So to begin with, I'd like to start with a lemma, which is not due to me, and it's a standard argument, is that there is indeed a pseudo-representation tau n comma delta n from GQNP to Tn rho bar, which lifts stress rho bar and determinant rho bar. So it gives a morphism from R rho bar PD to Tn rho bar, which we call phi, and it is surjective. So there is a pseudo-representation, first of all, taking values in Tn rho bar, which is lifting our residual pseudo-representation. So by universal property, we'll get a map from R rho bar PD to Tn rho bar. And it is the claim of the lemma is that it is surjective, and it's a very standard lemma. You just glue all the pseudo representations corresponding to modular forms, which modular eigenforms which lift rho bar, and you get this pseudo representation tau n delta n. And if you take an L which does not divide NP, tau n of Frobenius of L is TL, and delta n of Frobenius of L is L times SL. So therefore the map is surjective because the generators are in the image of phi. Okay, so this is a very standard result, but it is telling us that there is indeed, first of all, a map from R rho bar PD to Tn rho bar, so that we can at least compare them. And the next order of business is seeing when it is an isomorphism. So that is the main theorem that we are in. Suppose we are in the setup above, and in addition, suppose that this chi bar, which was chi1 bar times chi2 bar inverse. So rho bar was chi1 bar direct sum chi2 bar, chi bar was chi1 bar times chi2 bar inverse. So we suppose that chi bar restricted to GQP is not trivial, or omega p inverse restricted to GQP. Omega p is the p-adic cyclodromic, mod p cyclodromic character. So suppose chi bar restricted to GQP is not 1 or omega p inverse, and this Galois cohomology group H1 of GQNP comma chi bar, it has dimension 1, and P does not divide phi of n. Phi is the Euler function. Then the morphism from RPD rho bar to Tn rho bar, it induces an isomorphism between the maximal reduced quotient of RPD rho bar and Tn rho bar, and both are local complete intersection rings of Krull dimension 4. Moreover, if this other Galois cohomology group, the Galois cohomology group of H1 G cube comma NP chi bar inverse, if it has dimension between 1 and 3, then the map phi from RPD rho bar and Tn rho bar is actually an isomorphism. We don't even need to go to the reduced quotient. And both are again local complete intersection rings of Krull dimension 4. Okay, so this is the main theorem of my work. And it sort of establishes big R is equal to T theorems. So this reduced quotient is not that a big deal, because we know that Tn rho bar is also reduced. So it is expected that the map will obviously factor through the reduced quotient. So the natural and the deformation rings are not really supposed to be reduced. I mean, it depends on the context. So it's not clear if they're expected to be reduced or not. But Anyway, so I'd like to say that under this hypothesis, I do establish some big R is equal to T theorems. Some comments on the hypothesis. This P does not divide phi of n is not a strong hypothesis because I do have results for P dividing phi of n. But for that, I need to take a slightly higher level because it could happen that there are modular forms of level greater than n, but the primes dividing their level is same as the primes dividing n. Okay, so that's why, you know, when P divides phi of n, I have to be careful with what kind of Hecke algebra I want to choose, because there could be eigenforms of higher level but having same prime factors lifting rho bar, and then I'll have to go to that level and take that Hecke algebra, and then I have some RST theorems, but it was complicated to state, so I just stated it with this hypothesis: P does not divide phi of n. Chi bar restricted to GQP not being 1 and omega P inverse is not a big deal. It's not a very strong hypothesis. It's rather standard. But in a sense, the strongest hypothesis here is that the dimension of the H1 to be 1. That is really a strong hypothesis. And at the moment, I don't know how to remove it. And that does puts a lot of restrictions. I mean, it is still, I mean, again, it's good to have some big RST theorems under some hypothesis, but this hypothesis is kind of a strong hypothesis. You know, it would be better if you can get a hypothesis which is not as strong as this, because as you increase the level and if you fix chi bar, this H1 is bound to go, the dimension of H1 is bound to increase at some point. So therefore, you know, that's why it is putting a lot of restrictions. Otherwise that hypothesis is also fine. Okay, so under this hypothesis, as I said, that I have the reduced quotient of RPD rho bar is isomorphic to Tn rho bar, and when the other Galois cohomology group of chi bar inverse, it has dimension between 1 and 3, then the map is then we don't even have to go to the reduced quotient. The deformation ring becomes reduced and it is isomorphic to Tn rho bar, and both of them are local complete intersection rings of Krull dimension 4. You know that because they are big rings, it is called a big RST theorem. I have 3 minutes, so let me just give another result that I had promised in the abstract. It is about level raising of modular forms. So it's not really a corollary of this main result, but it's a byproduct of various methods that I use to prove this result. So, you know, it's like a corollary of some intermediate results, or it's a consequence of some intermediate results. So let me state a very special case of that level raising theorem. So we let P be a regular prime, which means P does not divide the class number of P zeta P, cannot be an even integer between 2 and P minus 1. L1 up to LR be prime such that P does not divide Li square minus 1. So none of these primes are 1 or minus 1 mod P. And either P divides Li power k naught minus 1 for all I, or P divides Li power k naught minus 2 minus 1 for all i's. So under these hypotheses, if k is an integer such that k is congruent to k naught modulo P minus 1, then there is a new form, level gamma naught of L1 up to LR and weight k such that the Galois representation rho f lifts one direction omega p power k naught minus 1. Omega p is the mod p cyclotomic character. So this theorem is saying that under this hypothesis, we get that if k is an integer such that k is congruent to k naught modulo P minus 1, then there is a new form f of level L1 up to LR and weight k such that the reduction of rho f is modulo P is actually the direct sum of 1 and omega P power k naught minus 1. Or in other words, f is congruent to the Eisenstein series of level 1 and weight k naught. So just some history. For R is equal to 1, this theorem is known under less restrictive hypothesis by the work of Billerey and Menares. Their methods are different from our methods. So R is 1 is just your level raising at 1 prime. So that is the analog of Ribet's level raising. And that is already known by Billerey and Menares. And they don't have the first hypothesis that P does not divide Li square minus 1. They don't have that hypothesis. And then they have proved the same theorem, but only for level raising at a single prime. But here we are sort of level raising at multiple primes. So this is in the spirit of Diamond-Taylor. It is similar to the work of Diamond-Taylor. And such results are not known, surprisingly. You know, they are only known for rho bar equal to 1 direct sum omega p. So for k not equal to 2, which we are skipping. And they are known due to Yu and Wang Erickson, but they also use different methods than ours. So for k not greater than 1, this level raising at multiple primes were not really known. And as a byproduct of the method, I could prove some such results. I'm out of time, so I'm going to stop here. Thank you for listening. Thank you.
And thank you, Shaunak, for a wonderful talk. Any questions, comments? So I have a question regarding your last slide. So can you say something about the Eisenstein ideals from the results you have shown? This thing.
Yeah, I have not explored that part yet because but yeah, it is.
Because this is what it is, Eisenstein ideal, right? There's a congruence between modular forms and new forms and Eisenstein series. This side you have an Eisenstein series, right? So
precisely. Yeah, you're right. I mean, I think something can be said about Eisenstein ideal, but I have not explored that direction yet. It's an interesting question, but yeah, I have not thought about it.
Okay, so any more questions? Comments? If not, let's thank Shaunak and thank you very much. So
thank you.
And we will meet in 8 minutes from now. The next talk is at 10:20.